So up to this point, we've pretty much used hypothesis tests as the mechanism for making statistical inference from our sample to a population. But there's actually another mechanism for doing so, and that is via confidence intervals. And a confidence interval or a confidence interval is really just another way of using the information that a hypothesis test uses, and we express the information that we have in a slightly different way. We are going to get the same results, but depending on how you look at it, we may actually get more information via the confidence interval mechanism as opposed to a hypothesis test. So you might notice that I might interchangeably use the terms confidence interval and confidence region. Confidence interval technically is for a one-dimensional parameter or for a single parameter. It's a range of plausible values for that parameter. And a confidence region is a multi-dimensional confidence interval. So it's a region that should contain two or more parameters with some level of confidence. And as I mentioned, a confidence region or confidence interval provides us with plausible values for our population parameters. So whereas with a hypothesis test, we essentially end up making a claim or deciding between two claims, for a confidence interval, instead of directly deciding deciding between two claims, we're just going to get a range of plausible values for our parameters. And from that range of plausible values of the parameters, we can then make our decision about what we think the true value of the parameter is going to be. And in terms of the interpretation of a confidence interval or confidence region, it has to do with repeated samples from our population. So imagine taking multiple samples, I shouldn't say multiple, I should say lots and lots and lots of samples from our population. And for each one of those independent samples, we construct a confidence interval or confidence region. And you have this confidence level that you get to decide. Let's say it's 95%. Well, then the proportion of intervals that we construct from our independent samples should contain the true values 95% of the time. So some of our intervals are going to contain the true population values. Some of the intervals are not. But the proportion of intervals that should contain the true population values is going to equal our confidence level. So just to give you a visual description of what I'm talking about, let me draw a quick picture here. So we have a population, and we're going to take sample after sample after sample of some certain size. So each of these samples is a different sample from our population, and so because of that, we're going to have sampling variability. And for each one of these independent samples, we construct a confidence interval. So we don't just get one confidence interval over and over again. We're going to get different confidence intervals because each one of these samples has different members of the population. And so the standard deviation, the estimated parameter values are all going to vary a little bit from sample to sample. Because of that, our confidence interval is going to move around. So let's say that we just had a single parameter value, single population mean, and it was equal to 0. Well, maybe for our first interval, it contained the population mean. The second interval does the same thing, the third interval, and so on. You can see these move around from sample to sample. And confidence levels are generally pretty high, and so most of these intervals should contain the true value. But then every once in a while, you're going to get an interval that does not contain the true population mean. We don't know which intervals those are because we don't know what the true population value is. If we knew that, we wouldn't really need to be constructing a confidence interval, would we? So we don't know which of our intervals is going to contain the actual population value, but because our confidence level is going to be high, usually 90, 95, 98%, we believe that our specific interval that we get for our sample is going to contain the true population mean. But when I say I'm confident that my interval contains the population mean, I'm not saying the probability that it contains the mean is, say, 95%. Because once I construct one of these intervals, this interval right here either contains the population mean or it does not contain the population mean. So the probability that this particular interval contains the population mean is going to be 1. It does in fact contain the population mean. And in fact, the probability for each of these intervals will be 1, except for this one right here. the probability that it contains the population mean will always be 0 because it doesn't contain 0. And so when I'm talking about confidence level, I'm not referring to the probability that a specific interval contains the population mean or the population parameter. I'm referring to the proportion of all possible intervals that I could get from random samples of my population that would contain the true population value. So my confidence level doesn't refer to a single interval, it really refers to the totality of all potential intervals from my population. So that's a really important distinction that you need to make in your mind. So the thing about these confidence intervals or confidence regions is that they are directly linked to hypothesis tests. So I mentioned that a confidence interval is really just a different way of using the same information. And you're not going to get different conclusions, you're just going to get different information, different way of making statistical inference. So the link is that if a point or if a value lies within your 95% confidence region, then at a significance level of say 0.05, we would fail to reject our null hypothesis of no difference from the values in your confidence region. So for each of the values in your confidence interval, you're going to fail to reject the null hypothesis that our parameter equals that value. On the other hand, any point, any value outside of our confidence region, if we did a hypothesis test for those particular parameter values, we would in fact conclude the alternative hypothesis. So we would reject the null hypothesis and conclude the alternative for all the values outside of our confidence intervals or confidence regions. So a confidence interval doesn't give us some of the same information that a hypothesis test does. So for example, we don't get a p-value when we construct a confidence interval, and we can only construct a confidence interval at a specific confidence level. And so we don't know what the results would be if we constructed an interval using a different confidence level. But confidence regions are actually often preferred over hypothesis tests because instead of simply making a decision between the null and alternative hypotheses, you actually have an idea of plausible parameter values, which is often more useful. And one of the reasons for this, so there's actually a big debate in the statistical community about whether hypothesis tests make sense at all. So I'm sort of under the persuasion that they are useful and helpful, though I can sympathize with some of the criticisms. But the idea is that, let's say we were just testing whether a population mean was equal to 0. So the null hypothesis is never actually true, even though we might fail to reject the null hypothesis and we might do simulated data where the null hypothesis is true. In real life, the null hypothesis is never going to be true. The question really is whether the null hypothesis is practically true. So for example, even if the null hypothesis were not true, mu wasn't actually equal to 0, maybe instead mu equals 0.0000001. And my suspicion is that in most contexts, whether this is true or this is true, you conclude the exact same thing. And so we're not really concerned with whether mu equals 0, we're really concerned with whether mu is close to 0. And so for that reason, people have a problem with hypothesis tests. So anyway, the point is that when we get our confidence interval, so let's say our interval runs from 10 to 22, then you can look at this and say, okay, not only do I think my population value is bounded away from 0, I in fact think it's more than 10. And then depending on the context, that allows you to assess whether the effect is large or not. So for example, maybe 10, in whatever context you're in, is not a big difference from 0. So maybe that's within natural sampling variability, for example. On the other hand, it may be that 10 is very, very different from 0 in your particular context. And so it not only allows you to make a decision between some sort of null and alternative hypotheses, it also allows you to get an idea of the effect size or the actual value of your population parameter, which is oftentimes what people are really interested in knowing anyway. So when we have more than one confidence interval, which should occur anytime we have more than one population parameter, we have to decide whether we should construct our confidence regions individually or simultaneously. So an individual confidence interval has a confidence level related only to that particular parameter. And if you look at the joint confidence level or the simultaneous confidence level of your confidence regions or your confidence intervals, then it's actually going to be less than that. So the point is that if I have one confidence interval constructed at a 95% confidence level, and I have another interval constructed at a 95% confidence level, if I am asking what's the overall confidence level that both intervals contain their parameter values, it's not 95%, it's something like greater than 90%. So there's actually something called a Bonferroni correction that helps you determine the lower bound for what the actual confidence level might be. But the point is that when we're making more than one statistical inference, that error is going to compound, and so we don't get the same overall confidence level for our confidence regions simultaneously. And we'll talk more about that in just a second. But in the meantime, there is a general form that most confidence intervals follow. And this is not always true, but especially when you're talking about something related to the mean of a population, you generally see an interval that's constructed after the fashion estimate plus or minus some critical value, which is just a number from some statistical distribution, multiplied by the estimated standard error of your estimate. And in our particular context, this, I guess we'll see it on the next slide, I believe. There we go. So in our particular context, this is the estimated regression coefficient plus the 1 minus alpha over 2 quantile from a t-distribution with n minus p degrees of freedom. So if you remember, under our null hypothesis, under the assumption of normal errors with mean 0 and constant variance, then we have the sampling distribution of each of our estimated regression coefficients is the t-distribution with n minus p degrees of freedom. And we pick the 1 minus alpha over 2 quantile essentially because we want the areas in both tails. So our confidence interval is essentially accounting for everything in the middle here, and it only doesn't account for the farthest alpha over 2 plus alpha over 2 proportion of events. So that's a total of alpha events that we're not accounting for, or that are more extreme than what we care about. And so our overall confidence level will be 1 minus alpha, since our confidence interval essentially has to do with this middle region right here. So we take the 1 minus alpha over 2 quantile from our t-distribution with n minus p degrees of freedom. We multiply it by this ugly thing right here. And this may look confusing, but this is just a formula here for the estimated standard error of that particular estimated regression coefficient. If you remember, the variance-covariance matrix of our estimated regression coefficients is sigma squared times x transpose x inverse. And so I want the standard error, so I take the square root of that. And this is just telling me that I want the information in row I, column I. And that's going to be the information related to regression coefficient I minus 1. And so this just tells us exactly how we get this standard error, how we calculate this estimated standard error. And this is the formula that we use for the individual confidence intervals of our true regression coefficients for each predictor variable. So I mentioned that we oftentimes have to decide between whether we want individual confidence intervals or we want some sort of confidence region. And just to sort of let the cat out of the bag, we in general are going to want simultaneous confidence regions if more than one parameter is of interest. So if we actually want to make some sort of simultaneous inference about our regression coefficients, then we really should use the simultaneous confidence region procedure. And this formula here is kind of scary, but essentially says that if we take the estimated regression coefficients, we subtract the true regression coefficients, and we do that as some sort of cross product with a quadratic form with x transpose x, then this quantity is going to be less than or equal to p, which is the number of regression coefficients, multiplied by the estimated by the residual standard error squared, so the estimated variance of our errors, multiplied by the 1 minus alpha quantile of an F random variable with P numerator degrees of freedom and N minus P denominator degrees of freedom. So long story short, we have this quadratic form here, which should be less than or equal to this upper bound with confidence level 1 minus alpha. And so you can actually solve these things. You can actually write this as some sort of elliptical equation in 2 dimensions or an ellipsoid in 3 or more dimensions. And this allows us to obtain our simultaneous confidence region. So that's really the punchline there. So this is the formula that you would use to construct a simultaneous confidence region for your true regression coefficients. And fortunately, plotting these regions has been made easy through use of the ellipse package. So let's just do some examples here of how we would construct these confidence intervals or confidence regions. So first of all, let's construct a 95% confidence interval for beta area, so the regression coefficient related to the area predictor, and this is assuming the other 4 predictors are in the model. So once again, the interpretation and the results depend on the other predictors that are going to be in our regression model. So I fit my linear model. I regress species on all 5 predictors, including the area predictor there. And I look at my misspelled summary of my linear model to get the information here. And the reason I do that is because, as we've already noted at some point in this class, the summary function provides us a lot of information about our estimated regression coefficients, as well as our population regression coefficients. So we have our estimated coefficients, we have the associated estimated standard error, and then we have the individual t-tests that we talked about earlier in this chapter. So for the area predictor, or I should say for the area coefficient, we have an estimate of negative 0.02394, and the estimated standard error is 0.02242. So we want to construct this individual confidence interval, and so I need the 1 minus alpha over 2 quantile from our t-distribution with n minus p degrees of freedom. And if you remember, the df dot residual function is going to grab the degrees of freedom of our residual the residual sum of squares, which is n minus p. So this is going to be n minus p degrees of freedom, but it pulls it out automatically so we don't have to manually type it. And this is going to be the 1 minus alpha over 2 quantile. So in this particular context, we have a 95% confidence interval. So it's a 0.95 confidence level. And I keep saying the 1 minus alpha over 2 quantile. So if this is my confidence level, then it implies that alpha is equal to 0.05. So 1 minus alpha equals the confidence level. And so that means that solving for this, we can easily see that alpha has to be 0.05. And so 1 minus alpha over 2 is going to be 1 minus 0.05 over 2, which is 0.975. And so even though the notation that the author uses is alpha over 2, this stands for the 1 minus alpha over 2 quantile, which means that we need to calculate 1 minus alpha over 2, 0.975 in this case, and use that to find the appropriate quantile from our t-distribution in R. So I calculate that quantile here, and so now I just put this in the formula, the estimate plus or minus the critical value from our t-distribution multiplied by the estimated standard error. So my 95% confidence interval ranges from negative 0.07 up to 0.022. And that wasn't too difficult to calculate, but fortunately, because this is something that people are commonly interested in doing, R provides the capabilities to essentially do this automatically. So that, in order to do that, we would use the comp int function here, and you can specify individual predictors if you want, or specify individual regression coefficients, but really there's no point in doing that. Usually we don't have that many predictors, and so it's easier to just use the comp int function on your linear model, and then it's going to calculate automatically the 95% confidence intervals for each of our regression coefficients. And so we get the same results here. So for area, we get negative 0.07 up to 0.022. And so we get the exact same results that we had when we constructed the interval manually. And if you want to change the confidence level, you don't want a 95% confidence interval, you can in fact do that. So I'll just look at the help file here. And so as I mentioned, you can specify specific predictors, specific confidence intervals, and so you would just set the parm argument if you want to do that. In general though, I would just leave it blank and it will automatically give you all confidence intervals for all the parameters in your regression model. And then if you want to change the confidence level, then you need to specify the level argument. So as you can see, by default it's 0.95, but if you wanted a 90% confidence interval, then you would say level equals 0.90. So we have a question here. So for what values of beta area would we fail to conclude the alternative hypothesis in a two-sided test using alpha equal to 0.05? So just to be very clear about what I'm asking here, we're testing the null hypothesis that beta area equals C versus the alternative hypothesis that beta area is not equal to C. And this is given the other parameters are not equal to 0. So I'm not going to write those all out. We've done this many, many times. But you would say things like beta S cruise and beta nearest and beta elevation, etc., are not equal to 0 on this right-hand side. So we're assuming that all those other predictor variables are already in the model. So this is the hypothesis we're trying to decide here. So I don't just have a 0, I actually have a C, and I get to specify what C is going to be. And my question asks, for what values of C would I fail to reject this null hypothesis at alpha equal to 0.05? And as we already saw from we already talked about previously in these slides, it's just going to be the values of my confidence interval. So if I look at my confidence interval again, I guess I already have that in the notes. It runs from negative 0.07 up to 0.022. So basically, for what values would we fail to reject the null hypothesis? So we fail to reject the null hypothesis for C equal to negative 0.07 up to 0.022, where really we should be a little bit more exact, but I think you get the idea. So basically we just look at the lower bound and the upper bound of our confidence interval here for our, for our confidence interval here. And that lower bound and that upper bound specify the limits of C that would cause us to fail to reject the null hypothesis for the test that we have right here. On the other hand, we would reject the null hypothesis for C less than negative 0.07 and C greater than 0.022, where of course we're not going to worry about the round off error here. You get the idea. So basically any values of outside of our confidence interval for beta area, we would in fact reject the null hypothesis and conclude the alternative hypothesis for this particular test. So I mentioned that we can construct simultaneous confidence regions for our regression coefficients using the ellipse package. And so that's what I'm going to do right now. So I load the ellipse package. Make sure you install that on your computer if you haven't done so already. And I use the plot function on the ellipse function of my linear model. So you take ellipse L mod, then you have to specify which regression coefficients you want to construct a confidence interval for. And you also have to specify the type of interval here. And we want a line. So basically we want an ellipse. We want the dots to be connected. So we do type equals L. You can specify the X and Y limits like you usually would here. This is just something convenient for this particular example. You'd have to mess with that yourself if you wanted to figure that out on your own for a different example. But this is going to construct an interval for the second regression coefficient and the sixth regression coefficient. And if I wanted to know which ones those were, I can just look at my L mod here. And so that's going to be for the area predictor, or for the area coefficient, so 2, 3, 4, 5, 6, and adjacent. So this is the confidence ellipsoid, the confidence region for the area regression coefficient and the adjacent regression coefficient. And then you notice I have some additional information here. So what am I doing with these? So I'm plotting a dot here at 0, 0. So I'm plotting a dot at the origin. And I'm also plotting a dot at the estimated regression coefficient. So at beta hat area and beta hat adjacent. And so and of course this is going to be in the center of my ellipse. And then oftentimes it's of interest of how that relates to the origin for our predictors. And then what I'm going to do here in the next couple lines of code is I am plotting the confidence intervals for each of the individual regression coefficients. So this is not, so up here I am producing my simultaneous confidence bands, and down here I plot the confidence interval for beta area, and I'm also plotting the confidence interval for beta adjacent. So the V here means make vertical lines at the values of the lower and upper endpoint of my confidence interval. And so you can see from our individual confidence, or on this graph here, we have our joint confidence region, and then we have our individual confidence bands. And so we see the individual confidence band here at negative 0.07, running up to 0.022, just like we calculated. And if we wanted to, we could look at the limits of the confidence interval for beta adjacent. Looks like it runs from approximately negative 0.11 up to 0.04. Double check that here. So negative 0.11 up to negative 0.04. So we can see the individual confidence bands are plotted on that same graphic. And what exactly do we learn from this? So this is the values of my estimated regression coefficients, and this is the origin here. So let's notice a few things. So one is that the individual confidence bands are narrower than the lower and upper limits of my simultaneous confidence region here. So I can see here that these horizontal bands here are within the smallest, or in between the smallest and largest values in the y direction, and we see a similar pattern in the x direction. So the individual confidence intervals are going to be narrower in general than my simultaneous confidence region. And that should make sense simply because when you're making your simultaneous confidence region, you're adjusting for additional uncertainty. So it has to be a little bit bigger than the individual confidence intervals. However, at least in this case, the simultaneous confidence region has smaller area than this rectangle right here. So that'd be something you'd have to figure out on your own. But the reason this happens is because the simultaneous confidence region, our estimated regression coefficients are correlated. And so that's why we get this ellipsoid instead of some sort of rectangle. So this helps us to make joint inference about our regression coefficients. And so that allows us to answer questions like this. So do we believe that beta area equals beta adjacent equals 0? So simultaneously, do we think the area and adjacent regression coefficients are equal to 0 after accounting for the other predictors? And looking at this graphic, we would be confident that the answer is no. So if in fact the two regression coefficients, it was plausible that they simultaneously were 0, then our region here should contain the origin. So it should contain the value 0, 0. But in fact, it does not. So because of that, we would conclude that the two regression coefficients do not simultaneously equal 0. Notice that does not mean that one of them, or that both of them are different from 0. In fact, it's perfectly reasonable for the area regression coefficient to be equal to 0. Here we can just see that from our x-axis. But for the adjacent regression coefficient, it doesn't look like 0 is all that reasonable. So that's some of the information that we have here. And what's interesting is that sometimes you can obtain different results for your simultaneous confidence interval in comparison with your individual confidence intervals. So look at the simultaneous confidence region here. We see that it does not contain the 0.00. But we can imagine that where I have this little hand here, that's actually the origin. And so you could see there that if that were in fact the case, our individual confidence intervals would contain the 0 values for both of them. So if we just look at the individual confidence intervals, we would say it's reasonable that the regression coefficients are equal to 0 simultaneously. But in fact, that location where the hand is outside of my simultaneous confidence band. So if the hand were the origin, we would get different results looking at our individual confidence intervals in comparison with our simultaneous confidence intervals, simply because our simultaneous confidence intervals do not contain that same point. And of course, it can work in reverse. So if the hand were right here, if this were the origin, we would say that it was reasonable for both regression coefficients to equal 0, because that point would be inside the simultaneous confidence region, but it would be outside this rectangle that intersects the two individual confidence regions. And so we don't necessarily have to get the same results for our simultaneous confidence region and our individual confidence intervals. And so you have to be very careful about that. So you don't just want to look at your individual confidence intervals to make your conclusion about what's going on with two or more parameters simultaneously. If you really want to make inference about two or more parameters simultaneously, then you really should construct a simultaneous confidence region using the ellipse package. And I should point out that if, for some reason, the individual confidence intervals were tangential to my ellipsoid here, so basically there'd be a vertical line here, there'd be another vertical line here, right there, there'd be a horizontal line running right there, and right there. If that were the case, then in fact these individual confidence regions would have simultaneous 95% confidence level. It wouldn't be as efficient, wouldn't use the information as efficiently as the simultaneous confidence region, but if in fact the individual confidence intervals were tangential to the confidence ellipsoid, then they would in fact have simultaneous 95% confidence level. They'd actually just be a little bit too conservative. So that's something to keep in mind. So as I mentioned before, just to reiterate it one more time, if you want to make inference about more than one regression coefficient simultaneously, you really should consider the joint testing procedure. You should really construct the joint confidence region, the confidence ellipsoid, and you shouldn't make your conclusions from your individual confidence intervals. So your univariate confidence intervals and hypothesis tests may produce different results than if you do simultaneous hypothesis tests, or construct simultaneous confidence regions.